welcome back for Arduino tutorial number 11. I know it's been a few weeks since my last tutorial. I had to catch up on some schoolwork and stuff like that, and I'm still working hard on that. So the next few tutorials won't come out consecutive weeks. I'm going to get them out as fast as I can, but I need to make sure I don't fail any of my classes to do these videos. But I'm going to do this one right now, and it's going to be on SD cards and data logging. So we're going to make a nice little data logger. I've already put one together and run some tests with it. This is the data logger that we're going to end up with today. We're going to be using an Arduino Uno, an SD card shield from cooking-hacks.com with a micro SD card. We'll have a temperature sensor, a light sensor, and I also put 2 infrared distance sensors in the back. And aside from the SD card, these are all things that we've worked with before. So I won't go too heavy into the code for these or into the descriptions of these parts because we all know how they work already. So what I'll focus on is actually implementing some of the code, testing it out, and getting the data off the SD card and doing cool stuff with it. And I'll cover both reading and writing with the SD card with the Arduino. And yeah, it's a pretty extensive set of knowledge required to put this together. So if you haven't watched my first 10 Arduino tutorials, now is the time to do that. Specifically, the SPI tutorial will be useful because that's how we communicate with the SD card. The I2C tutorial will be useful because that's how we'll communicate with temperature sensor. And the analog input tutorial will be useful because we'll use that to grab data from our infrared distance sensor as well as our photo sensor for detecting the light levels. Alright, so that's what we're working with. Let's take a look at the circuit that we're going to need to put together. We'll do a little block diagram to see what we need. And then we'll get started programming it and testing out the data logger. The first step with any slightly larger project like this one is going to be to draw a block diagram so that we know what we're working with and how we have to hook everything up. Now to start with, I'm just going to hook up the SD card and we'll learn how to program it first. And then we'll go back and revise this block diagram to add additional sensors that we can log onto the SD card. So to start off with, all we're going to have, very simply, communicating via SPI, is going to be an SD card. That's it. And we'll debug to a computer using simple serial connection as we've done many times in the past. And that's basically it. That's how we're going to start. Just an SD card hooked up via an SPI interface to the Arduino, and we'll debug it with serial to the computer. It's important to note that SD cards operate at 3.3 volts as opposed to 5 volts like the Arduino. So we'll use the onboard regulator that's already on board the SD card shield that we're using to regulate the 5 volts from the Arduino down to 3.3 volts to power the SD card. So let's get this set up so we can start testing the SD card. Here we have our Arduino Uno as well as the SD card shield that we'll be using. I've already put the micro SD card into the slot here and we're ready to put onto the Arduino. This particular SD card shield can be utilized in 2 ways. You can connect the pins over here to digital pins 8 through 13, or you can attach the in-circuit serial programmer to the connector right here. Both of them provide the appropriate SPI pin connections. The only difference really is that if you decide to use these, it makes it a little easier to put shields on, or different shields on in addition to this one. And it also means that you have to set the power pin high for pin 8 because we'll be using that to power the device directly off of one of the digital I/O pins. There's also a jumper that you use to select which interface you'll be using. I'm going to choose to put it on the digital pins 8 through 13 to utilize it. Great. The very first thing that we're going to do to test out the SD card is we're just going to try writing it some very simple data over and over again about every 5 seconds. And then we'll read the data with the computer to confirm that the Arduino wrote data successfully to the Arduino. Then we can start doing some more complex stuff with it. I've already started our program out here. First off, you have to include the default sd.h library. It comes with the Arduino programming environment. So make sure you include that. Next thing is we have to set any pins that we're going to need to set as inputs and outputs. So you need to change the chip select pin. That's going to be pin 10. You always need to set that whenever you're using SPI, although 10 is generally the default if you remember from our SPI tutorial. And we're going to define the power pin. And remember, as I said before, I have the SD card shield plugged into digital pins 8 through 13, and 8 is just going to be passing 5 volts of power to it by sending in a digital high, and that'll give it 5 volts. So we'll define the pin that we'll use for power. In the setup function, we'll start a serial process so that we can send serial data back to the computer to see what's going on. So we'll start the serial communication and just let the user know that we're initializing the card. Next up, we'll set the chip select pin as an output because we're going to need to toggle that high or low when we're reading or writing data to the SD card because you could potentially have other SPI devices on the same bus, although we don't at the moment. And next thing, we're going to draw power from pin 8 so that the SD card has power to read and write. And now let's fill in the rest of this program. So the first thing is we're going to have to check if the card is ready. And remember, you can figure out all these functions for the SD card if you just go to the Arduino website and look at the sd.h library. They explain all these. But I'll show you how to get started here. So the first thing we're going to have to do is check to see if we can actually write to the SD card by running sd.begin. And in one fell swoop, we're going to run sd.begin and check to see if it was successful with this command. So what this is going to do is it's going to begin an SD card process, and while it's doing that, if that for whatever reason returns value of false, which it will if for some reason it can't succeed, like it can't connect to the card because we plugged it in wrong or something like that, this will return a false, and we can check for that to show the user that there's been a problem. So if this is the case and it returns false, we'll do serial.println card failed. That way the user knows that something is going on. And by putting a return statement right here, this will just end the program right here. So if the card fails, there's no reason to go run the loop or anything like that. It's not going to work. So we're just going to return and the entire program is going to terminate. That's going to happen whenever you put a return statement. Okay. And then we're just going to, if that didn't give an error and it didn't return, then it means the card's ready. So let's just let the user know. Serial.println card ready. Great. Okay, now let's fill in the loop. All I'm going to do is print the word hello. You can pick any word you want. Maybe you want to write Jeremy is so cool. And I'm just going to print that over and over into a text file every 5 seconds. So the first thing that we need to do here is we need to make something of the structure type file. So we'll do file, and we'll just call it data file. It's going to equal sd.open. You'll specify the file that you want to write to. It does not have to exist yet. If it doesn't exist, it'll automatically create it. So I'm going to call it log.txt. Make sure you put it in quotes because it's a file name. And the second parameter is optional. If you don't put a second parameter in, it'll only be able to read from it. But if you do put the second parameter in, you can specify that you want to be able to write to this file. So we'll specify that. Okay. We now have something called data file, which is a type file that opens on the SD card log.txt. You can only have one file open at a time for writing. So once we're done with this, we'll close it so we can use another file if we so desire. So let's first see if we actually managed to successfully open it. It's important to do error checking like this so that when you're running this in the field, you can account for potential issues that might arise. Okay, so data file dot println. If we were able to connect to it, of course, we'll just print the data string to it. So this works very similar to the way you print stuff over serial. We have the println command, just like we can do serial.println, we can now do datafile.println. So we'll print data string, which you defined earlier, just onto the next available line in the text file. And it's as simple as that. And then once we're done, we want to make sure that we close the data file so that at some point later we can open a different file. So close it. And now for debugging purposes, I'm just going to print to the display window the exact same thing that we just added to the text file so we can keep track of our program. Okay. And now let's handle the other case. So this is assuming that data file was created. If data file couldn't be created for some reason, we need to handle that case. So we'll make an else statement. And in there, we'll tell the user that we couldn't open or create the log file. So we'll do serial.println. So remember, serial is sending it to the computer. Data file is sending it to a file on the SD card. We'll do serial.println. Couldn't access file. And that should be just about it. There's only one more thing that we have to do here, which is to put our delay 5,000, which I've already done. So remember, we were working in milliseconds here, so 5,000 is a 5-second delay. And what this means is that it'll wait for 5 seconds, then go back, and then write it another line into the SD card. So let's see how this works. So the file's been uploaded to our SD card enabled Arduino. Let's open up the serial monitor. Great, it says that it's initializing the card ready, and Jeremy's cool. In a few seconds, it'll print it again, and it'll keep doing this every 5 seconds. Now, I'll take the SD card out of the Arduino, plug into the computer, and show you that we can actually read the data right off the text file that we've just saved onto the micro SD card. I've now taken the SD card out of the Arduino and plugged it into my computer, and we can see it did indeed create the log file, so let's open it up, and sure enough, there's all the data that we wrote to it. Alright, awesome. So next up, let's delete that. We can recreate it later through the program. And now I'm going to add a text file to my SD card. And we're going to use this to read data from the SD card. So I'm going to make a file called commands.txt. And in here I'm just going to put one simple value, 1,000, let's say. And what we'll do is we'll read this out, and we'll use this in our program as a delay between when it writes data to the SD card. And this will allow us to dynamically change the program without ever actually having to plug the Arduino in and reprogram it. You can change the way the Arduino works by simply adding a bunch of commands here and then interpreting them with the Arduino to do something different. Okay, so now let's put this card back in the Arduino and we'll see how to read the data off the card. Alright, now I've gone through and started to modify our original program to read the data off the SD card. First thing I did was define a new float. Float just meaning that it has a decimal value potentially, and you'll see in a second when I do the math why I have to do that. That's going to define the refresh rate. So before we just hard-coded it as 5,000 or 5 seconds, and that will be defined by the value in text file, which if you remember we set to 1,000. So the beginning of the setup is all the same. We're just going to connect to the SD card, etc. But now we have to add another thing to the setup, this part here, that reads from the configuration information on the SD card and sets the variables appropriately. Now the way SPI or any serial form of communication works is 1 byte is sent back and forth at a time. So we can't just read the number 5,000 off. We actually need to read it byte by byte and then reassemble it into the number 5,000, 1,000, whatever it is. So the first thing we'll do is just like we did before, we're going to create a new file type called command file, and it'll be commands.txt. And before where we had to put read file, we don't have to do that, or write file, because we're only going to be reading from it. Again, we'll have an if statement to check if the command file was actually found. And if it was, we'll let the user know that we are now reading the command file by printing it to the serial terminal. Now what we have to do is actually figure out what the number is that's printed there. And that's actually a little bit more challenging than it seems. You have to come up with some clever math to do that, and that's what this is doing right here. So the first thing I'm doing is I'm defining the decade. The decade being just essentially the number of digits that are in the number. So for a value of 1,000, the decade that it starts with is going to be 1,000, and then if it was 500, the decade would be 100. It's basically just the number. It's basically representing the size of the number in decades of 10. So if we to do that, to find that value, all I'm doing is I'm saying the power, so this is doing the power, so 10 raised to this value, which is the second argument of the power function, which is a math function that's included with Arduino. And what this is doing is this is looking at the command file and getting the available number of bytes in it. So the available number of bytes, if we have 1,000, a value of 1,000 in there, there's going to be a total of 4 bytes because there's 4 digits in the number 1,000. So it'll return the number 4, and then we'll subtract 1 from that. So that'll be 10 to the 3, and 10 to the 3 is 1,000. So that's giving us the decade that we want. But it could very well be 5,000 or 3,000. All we know is that it's 1,000 times a singular number between 1 and 9, basically. We know that it's in that decade order. So the next thing we're going to do is while the command file has bytes available. So we're going to step through it byte by byte. We're going to take the float. We're going to take a float that we're defining as a temporary float and set it equal to that current byte. And if you remember from the serial communication tutorial that I did a while back, we can get that byte as a number. Remember, it reads it in as a char, but we want it as a number by just subtracting the character equivalent of 0. So this is going to read the first byte. The first byte will be a 1 because we use the value 1000. So it's going to be 1 minus that byte value so that we actually get a float out that's going to be 1.0 basically. Now the refresh rate, which we defined up at the top to start as 0, we're going to update that refresh rate. So we remember we started the decade at 1000. So what's going to happen is this temp value that we just got out, we got a 1. So this is the first digit is a 1. Temp is just giving you that digit. We're going to multiply 1 by the current decade. So we're going to multiply it by 1000. And then we're going to add it to whatever the refresh rate current is. So it starts at 0. So right now, refresh rate equal to 1000. And we actually already have the number we need. But we don't know that. We could have entered a number like 1324. So we need to accommodate for that. So the next thing we'll do is we'll divide the decade by 10. So if it was 1000, it now goes down to 100. We'll read the next byte. The next byte is a 0. And now the refresh rate will equal what it previously was. So 1000 plus 0 times the decade, which is 100. So it's just going to be 0 again, and you're going to end up with 1000 after you finish going through this loop. So this is just a clever way to read out a number easily from a sequence of bytes. And you can imagine how this would work if we had a more complex number like 1300, let's say. The next number that came down would be a 3. So we would get the 3 as the temp value. We'd multiply it by 300 because we just decremented the decade from 1000 to 100 by dividing by 10. So we would have 1000 plus 300, and we would have 1300, the number that we want. So that's how we get the integer out of it. I know it's a little confusing. If you have any questions, feel free to ask me. So now we can print to the user, this is the refresh rate. Awesome. Otherwise, we have to say we did not read the command file, and just like before, we'll return, completely ending the function if it can't find that command file. The data string can be exactly the same as before, and all this is actually pretty much the same. The only thing that we're going to change now is we're going to change the delay instead of being a hard-coded 5000 to refresh rate. Okay, and that should do it. Let's compile it and see if it refreshes the data just a little bit faster. Okay, so we can see that it's loaded up. It's read the command file properly. It knows that the refresh rate is now 1000 milliseconds. Keeping in mind that I had to use a float here because we're dividing by 10. And you can't be sure that it's a number that's divisible by 10, although technically it should be. You could potentially run into issues. And it's definitely refreshing once every 1 second now instead of 5 seconds. Great, we can now read and write from text files. We're ready to make the final code that will implement our data logger. Great, we've managed to successfully get the Arduino to communicate with an SD card over an SPI protocol, while simultaneously sending debug information over serial to the computer. We're ready for the next step, which is to add some sensors, whose information we can then record to the SD card. We'll use a light sensor, just a standard photo detector, a temperature sensor on the I2C communication bus, which we've learned about in a previous tutorial, and 2 infrared distance sensors. And we'll feed all those into the Arduino as analog values and record them in comma-separated value format to the SD card, which we can then read with Excel, MATLAB, just about anything you want to visualize all the awesome data you've acquired. So, let's get that circuit set up, and then we'll program it on the computer to get it recording some data. I've gone ahead and wired up the circuit for us. We've got the same Arduino as before, with an SD card reader mounted on top of it. I've fastened the Arduino to the breadboard by actually running some wires through the holes that hold it in place and just popping them into some breadboard holes, just to hold everything together on the breadboard. Here I have the light sensor connected through a 10K resistor voltage divider into the Arduino. Don't worry, I'll have all the schematic for this available for download so you can see it in schematic form. Here's our I2C temperature sensor. We have the pull-up resistors that are working on the I2C bus, and then 2 I2C lines that feed into those inputs on the Arduino. If you remember correctly, they are analog inputs 4 and 5 on the Arduino. Then we have the 2 infrared distance sensors, which I actually have mounted to the back of this plate. You can see the wires going to them. And those feed into 2 of the analog inputs as well. So we're using 5 of the analog input pins, 2 for the infrared distance sensors, we're using 1 for the light sensor, and 2 for the communication lines of the I2C bus, because those analog input lines are multiplexed as I2C communication lines. So that's basically it. The only other thing to note here is that this system is going to require a fair amount of power because of all the stuff running on it. So when you actually start logging data, you're going to need to use a 9 to 12 volt power adapter like this one. You could also use a 9 volt battery. The reason being is the USB port is not going to be able to supply enough current for us to run correctly. And I actually found that trying to run this over the USB port, I was reported incorrect values from the I2C temperature sensor due to a lack of required current to run the entire circuit. Plugging this in fixes it totally, and you'll want to do that anyway because the whole purpose of this logger is to run it without a computer. What's the fun if you have it plugged in by USB? Alright, now that we've got this wired up, we'll go write the code for it. And remember, you can grab the schematics for this from my website. So now that we've actually managed to find a way to read and write from the SD card, that was basically a new material. So I'll just walk you through the code that I've already written that grabs the data from the various sensors that we've hooked up, concatenates into a string, and then spits it onto a file on the SD card. Now instead of using a text file, I'm going to be using a comma-separated value file, or a .csv file, because it can be easily read by a program like Excel to make pretty graphs and stuff like that. So here's the changes that we had to make. First off, I'm now importing the I2C library because we're using an I2C temperature sensor. I'm defining the pins that I'm using for various analog sensors, including the IR pins and light pin. I'm defining the temperature address of the I2C temperature sensor, because if you remember on I2C communication buses, you identify devices by their ID. And I'm starting a value called ID equals 1 that will put at the beginning of each piece of data that we read. So we'll read data once every second as specified by our command file. And we'll assign each set of data an ID, and we'll increment that ID as we go, so we can see how many pieces of data we've recorded in total when we look at the outputted file. Most of the setup is basically the same. The only thing I've added here is at the end, after we've read from the command file and stuff like that, we're going to write to the top of the log file with header information. So instead of just writing raw data, at the top of it, we'll provide information about what each column represents. So we're going to write each of the columns in this order: ID, then light data, temperature data, and then each of the infrared distance sensors. So this basically just makes a heading for each column that tells us what data below is corresponding to. Okay, so that's basically it for the setup. And now all the loop is going to do is every time that we hit our refresh rate, we're going to go through and read the data from all the sensors and save it to a new line in the data file. So reading the light level is easy. That's just a simple analog read. Reading the temperature is copy-pasted directly from my tutorial on I2C communication. So this is just taken right from there. And all this does is it reads the current temperature value and then converts it to degrees Fahrenheit from the I2C temperature sensor. And then lastly, we're going to read the two distance values from the infrared distance sensors. Now that we have all the values, we're going to concatenate them into one string that we can write to one line of the data file. Each piece of data will be separated by comma, hence why it's called a comma-separated values file. And we're going to concatenate them together using simple plus signs. We convert them to strings first with this command, string, because we want to concatenate them all together into one string that we can then write easily, whereas right now they're integers. So we'll convert the ID to a string, write it, and then put a comma, and then we'll put the light level, then comma, then temperature in Fahrenheit, another comma, then the infrared distance value, and then another comma, and then we'll finish up the line with the second infrared distance value. So now we have a piece of data that we can write to it. This is equivalent to before just writing Jeremy is cool. All right, now we're going to open the log file, which I've changed from log.txt to log.csv because it's a comma-separated values file. And we're just going to write that data string that we just created. So data string is that concatenation of data that we just put together. And we're just going to write it to a new line on the SD file. And that's it. The last thing we have to do is increment the ID number so that next time, after the first time it'll print 1 here, the second time it'll print 2, etc. So we can identify each of the readings. And then they'll just wait for the set refresh time. So if we set it as 1,000 in the command file, then it will take new samples approximately every 1 second.
It's not exactly every 1 second because it takes a little bit of time to run all of this here. But basically we'll be taking a sample about every second. And that's it. So we'll upload that now, and we'll set up our data logger to grab some data over a 24-hour period, and then we'll come back and check on it and see what kind of stuff it got.
Okay, now that we have it all programmed, I've gone ahead and wedged it into my window over here. And I have 2 infrared distance sensors facing in towards the room, and then facing out towards the window is a light sensor and a temperature sensor. So my hope is I'll run this for 24 hours now and see how my movements within the room correspond to the change in temperature basically inside the room. I guess I won't detect it outside too much, although it's next to a window, so it'll probably fluctuate a little bit. But more importantly, the time of day outside. Now, I'm not sure if a 1 second sampling rate is actually sufficient to capture a whole lot of movement in the room. So we might not see a whole lot of data from the infrared distance sensors. It'll depend how much I move in front of them. To be honest, I'll probably be in class all day, so who knows if we'll get any data from them. But more importantly, you'll definitely be able to see the change in light levels outside over the course of a day. So let's go ahead and plug this in. I've already gone and removed the log file, so we're starting fresh with it. So all we have to do now is plug our power in, like that, and we're all ready to go. It's now recording, and if you look at the back of it, you'll be able to see that the transfer LED on pin 13 is blinking once every second to indicate that it is grabbing data. So let's let that run, and then we'll come back and see what kind of stuff we got.
I've gone ahead and run the system for almost exactly 24 hours now. I started it at 11:30 at night and turned it back off the next night at 11:30. So there's 24 hours of data here, and we can open up the CSV file on the computer. I suggest you save it off the SD card onto the computer in Excel, and you can see we have our nice row headers here and the data that's taken at each data point, as well as an incrementing ID. We can scroll through, and there's a ton of data here. And this is only taking up a tiny amount of memory too. That's a 2 GB SD card. I could have probably taken samples once every 5 milliseconds and still had more than enough space on here. But anyway, once every second is fine, and this is the data we have. So let's go ahead and graph it to see what kind of stuff we actually got out of here. And I'm sure there'll be a few anomalies. Nothing's ever quite perfect, but we can average those out using some moving filters. So we'll go to insert a linked scatter plot. It should generate one from the data. Okay, cool. So we can see right off the bat that the blue line here is marking daylight, and that's obviously during day hours, and I started it at nighttime. You can see when it went up here from the light in my room because I hadn't gone to sleep yet. And then when it's down at the bottom is when I was sleeping. So first off, there's a ton of data points here. So let's grab each of these and format the data series to remove the actual points on them, because they're kind of in the way and it's a little annoying. Alright, that's a little bit better, right? Alright, so we've removed all of the data points. Now the next thing we want to do is temperature is on a different scale than all these. So temperature is an actual degree value, whereas light, IR1 and IR2 are just analog values from 0 to 1023. So let's adjust temperature to put it on a separate y-axis value. Format the data series, put it on a secondary axis. Okay, cool. So now the right axis just corresponds to the red line or the temperature. And so we can see how that fluctuates. It obviously got warmer at this point during the day. Right when the sun was at its peak, so that makes perfect sense. And there's a bunch of anomalies in here. That's just due to random bad readings from the I2C temperature sensor. It's going to happen occasionally. Luckily, we can filter those out by putting a simple trend line in here and using a moving average filter. So we will add a trend line on a moving average, and you can see it's already a little bit better, but the period of 2 is way too small. Let's do more like 100, and that'll filter out all the weird values that we've got going on. Okay, that's looking better, but that's obviously too much. Let's try 10. That's looking pretty good. Maybe a little bit more than 10. Okay, that looks pretty solid. So now, why don't we just go ahead and turn off the red line entirely, because it's not really helping us very much. We want the best fitted line anyway. So we'll go to line color and turn it to no line. Okay, great. And now black is representing our moving average of the temperature. Infrared distance sensors are measuring basically movement in the room. Again, there's probably some anomalies in there too, and we can put a moving average filter for those to check for them. But I don't know, I was in my room a couple times during the day. This could very well represent me moving in or out. It could represent the blinds over the window blowing back and forth, things along those lines. It could even represent things like shadows moving across the room. Okay, but the key point here is that we can see all the information very clearly. This started at around midnight and ended at around midnight, and it's very clear that in the middle of the day it was sunny out because this is the light sensor. There was also a temperature peak in the middle of the day. That makes sense because the sun was at its highest and it was gloomy in the morning and got sunny in the afternoon. So it makes sense that it'd be a little warmer and then it'd stay a little bit warmer until I turned it off. That could also have something to do with the heating in my apartment turning on. The infrared distance sensors, as I kind of expected, didn't really do very much because I didn't move in front of them a whole lot. So they're mostly just picking up some random noise from various things fluttering around in the room and stuff like that. Nothing too interesting. But it's pretty clear that we can do some really neat stuff with this, and now we can track this over time. And in future tutorials, I'll show you how you can get real time from the internet or from GPS satellites and things like that. Alright, great. So we have our data logger now. You can hook up any kind of sensors you want to this and get really cool data out of this and then plot it and do whatever you want. So awesome. I love to see what you guys managed to put together with this data logger functionality.
Thanks guys for watching this episode of my Arduino tutorial series. I hope you enjoyed it. As always, if you have any comments, suggestions, questions, etc., please feel free to post them on YouTube, on my blog, jeremyblum.com, or on Element 14, and you can find all the schematics, source code, and parts list on both my website and on element14.com. Thanks again to cooking-hacks.com for supplying the shield that I used to make this video, and you guys can look forward to at least 4 more videos before May 31st on a variety of cool topics that should be pretty fun, and I'm looking forward to making them. So yeah, if you have any questions or anything, let me know. Otherwise, I'll see you as soon as I can get the next video out. Thanks for watching. Thanks to Element 14 for helping me to sponsor this video series. They were kind enough to provide a lot of the materials that I'll be using to create these tutorials. Feel free to go visit their website at element14.com. Check out their community, which is a great place to talk to people about electronics, the Arduino, and basically anything else engineering related. And they also have a store where you can buy a lot of the parts that we'll be using in these videos.